Okay, started the stream.
Okay.
Let me grab the link. Okay, started the stream. Grab the link. Okay, let's open it up. Could you let everyone through, please?
Sure.
Okay, 1 second. All right. Where's my chat window here? Morning, everyone, although it's not really morning anymore. Okay, so I put a link to the stream in case there is malfunctions. You should just grab it and just in case. We have 5 minutes before class starts, and I'll take questions about the assignment. This is the last class that we're going to have before the assignment is due. So let me start taking questions about the assignment.
Sir, for question 5, I just want to be clear. Do you want us to list out every single possibility for the
So
partition?
there were a lot of questions about this on Piazza. Have you checked Piazza?
I have checked Piazza, yes,
Okay.
but I just wanted to make it clear because it didn't come off as very clear.
So this is the thing. So you may have certain, I'm speaking you, I'm not just saying you to you, I'm meaning everyone here. You may have some expectations about the format of what a question should be like, right? So you're uncomfortable with the fact that I asked you a question and then you can see that maybe you don't want to write them all out. And so then you want to ask, well, okay, maybe there's a mistake in my question, right?
It's
because you
just
don't think that it would be pleasant to write them all out. Did I say that you needed to hand write them all out?
No.
So then,
okay.
I'm not going to give you more constraints. Okay, you're unhappy when there's less constraints, but I'm not going to give you more constraints. You just have to answer the question and move on. You have a lot of other work to do. Just answer the question. You know, everyone is concerned about, can we use this? Are we allowed to use that? No, don't. Just solve the question however you think is a proper solution. And then we're going to mark it. And then you'll find out what happens. That's the way it works. Okay, other questions?
I had one sort of small question. I think I may already know the
Elliot, go
answer.
ahead.
Just for I guess the general expectation for all questions, whether or not they ask for like proof or explanation, is that they're given like explanation. For example, like the power set question asks what is the cardinality of the power set of some set with cardinality n, but it doesn't ask to like prove it as well. It just sort of asks you to what is the answer. But I assume the assumption is to also, based on what I saw in Piazza, is also to prove it.
So you, when's the last time you looked at the question?
Yesterday.
Okay, because what you just said isn't true. It doesn't just ask what is the cardinality of the set. It says give clean and clear arguments for both answers.
No. I'm talking about the it's question 6. So like the it's, for example, it says it's the power set question. So
yeah, you can just answer the question however best you think you should answer it.
Okay.
Yeah. I don't. Yeah, the thing is that you shouldn't concern yourself at this point by the technicalities of the wording of questions. Just answer the questions. Don't worry so much. Don't worry so much. We're not here to nitpick. Yeah. Okay, keep going.
I had a question regarding how we can
Yeah.
represent maps. Like,
Yeah.
can we just use the notation of like 1:1, 2:2, 3:3 to represent a map like that? Is that allowed?
Well, I mean, you can use whatever notation you want, but why not just use the standard notation?
And like, if you could like please go through the notation once. I mean, I think I missed it last time.
So if you have a map, is there anything confusing about this notation? This is telling you what information?
Yeah. From which like the domain of the map and the codomain of the map. So
yeah, that's what it's telling you, and it's also giving you the name of the map, which is f.
Yes.
But it's not telling you what the map is doing, right? Mm-hmm. So if you had a specific element inside here, you could send it to f of x. You could say f of x is equal to such and such. You could say that f is the map defined by, you know, f of x is equal to ... You could do that, or x goes to ... Those are the standard ways of writing.
All right, thank you.
Okay.
Can we be given half points?
No.
Okay.
Professor, concerning the notation, I'm not sure how to like show using notation for one of the questions, the associativity. Like, how do I go from one function to another? I don't know how to show that by notation. So like,
maybe your question is about, so yeah, your question is kind of about the condition. So let's say that I have
just to be clear, like,
just for example, suppose that I have a set X,
okay,
and I have two subsets. Suppose I have two subsets of X, right? And I want to show that Y1 is equal to Y2. Okay, how would I show that? Well, one way to show that is to analyze. In other words, to break the question down into simpler pieces. So instead of proving that the subset Y1, instead of showing in one step that Y1 is equal to Y2, what you could show is that Y1 is contained inside Y2, and the other one, and then you could show that Y2 is contained inside Y1, and these two together would imply that Y1 is equal to Y2. So That would break your proof of the two pieces. You could say, let X be an element in Y1, and then show that X must be an element of Y2. That would establish this, and then if you let Y be an element in Y2, prove that it is an element of Y1. Then you would have that for every element in Y1, it's contained in Y2, and for every element of Y2, it's contained in Y1. That would prove equality.
No, I understand that part. No, I meant like.
I'm not finished. Okay,
Oh,
so
sorry.
if you have two maps, let's say that you have two maps from X to Y. Turn off your, mute yourself for a second.
Oh, sure.
Suppose you had two maps, F and G, from X to Y, right? And suppose that you wanted to show that they're equal, right? Then what does that mean? That means that F and G have the same domain and codomain, so that's good. That's number one. Okay, number two, we need to check that every element in X is sent by F to the same thing that G sends it to. So in other words, you have to show that for all X in X, show that F of X is equal to G of X. So that's like, you could think of it as iterating over all possible elements inside X. And that would prove, if you can show this, then this would prove that the functions or the maps are the same. Okay, so in that question, what you have on the left-hand side and on the right-hand side is a map. You have to show the equality of two maps. One of them is a composition of maps, and the other one is a composition of maps. Right. So you just need to understand, how do I take three maps, and how do I construct the new map, which is the composition of those three, in one particular order? Then you're going to get a new map. That's the map on the left. And then you do the same thing. You construct another map, which is the one that you get by, composing in the other order. And then you'll get another map. And these two maps you need to show are the same map. And so you need to use this procedure here for that.
Let's see. Okay, I'm concerned just about like the notation of it. So like G composed F, how would I like show that? G composed F normally.
So G composed F, okay, is a map. It's the composition, and we gave the definition for it before, right?
Yeah, so I understand what it means. It's just like the notation of like going from F to G. I'm not sure how to write it down. That's all.
You're not sure how to write this composition down?
Yeah, I want to be clear on how it's written. That's my question. That's all.
Yeah, I'm not sure you know how to answer that question. So for example, if you look at this picture here, so F and G, F maps from S to T, G maps from T to U. So the composition of F and G maps from S to U, and it takes an element in S to G of F of X. Okay, so the notation is that G composed with F applied to X is F of X and then G of that. So that's all the notation that you should need. There's no other hidden notation.
I see.
Okay.
All right. I just wanted to be clear on that point. Thank you.
So do people not see the top of the chat? Okay, anyway. Any other questions?
I just had a very, very small one.
Yeah, go ahead.
Okay, so my question is that if we had some element A in the codomain of a map, and we were considering the pre-image of that element, and we used the F, like inverse -1 type thing, brackets of A, is that already implicitly considered a set? So can we take that one piece of notation?
What is F inverse of A?
That is all of the values in the domain that map to.
Okay, but what is it as an object?
It is a set already?
Well, why are you asking me as a question when I ask you for an answer? You just said
in fairness, I
F
asked
inverse
for
of
an
A.
answer and you asked
F
me
inverse
to-
of A is the set of elements in the domain,
Okay,
which are mapped to A, right?
yes.
So yes, it is a set, but it's not just a set. What else is it?
The pre-image of A.
Well, yeah, that's true, but it's a subset of X. It's a
Yes.
subset of the domain. It's not just a set, but it's a
Okay.
subset of X.
Okay.
Okay.
So, yes. What I was really just asking is like, could we use that with the set notation? So for example, could we use the like absolute value bars for cardinality directly around that?
Of course,
And
because it's a
have-
set.
Okay, yes. So we don't have to say like, let X equal this set that is the pre-image of A or
No,
whatever.
F inverse of A is a set.
Okay, sounds good.
Okay.
Sir,
Yeah.
I just had one quick question regarding the notation like in terms of preиmages. I was wondering if it would be more appropriate to use curly like brackets as opposed to parentheses to like f of inverse the curly braces A close curly braces. Would that also be a valid form of notation to represent like the preimage of A on F, or I was just wondering if that was fine
You
as
want
well.
this?
Like, yes.
No,
No? Okay.
you could do this if you wanted.
Oh, okay, I see. Okay. That makes sense. Thank you.
Okay, that's it. Let's start. Okay, so last time we talked about properties of maps, injective, surjective, bijective. We talked about subsets. We talked about operations on subsets, union, intersection, talked about the power set. And we discussed this idea of a preimage. And the nice thing was that what we saw was that anytime you have a map, it automatically gives a partition of the domain. Okay, so let's continue with that observation, and let's see where it goes. So given a map from X to Y, we get remember that the image of F is the subset of Y such that there exists some point in the domain sent to it. Okay, but the other interesting thing is that we get a partition So the first thing we get is this subset of Y. But the next thing that we get is a partition of X into preimages. Okay, so in other words, so this partition P, what is it? It's a set of subsets of X that kind of cover all of X, right? So we need a bunch of subsets in X. They don't intersect with each other, and their union is the whole space, right? So it's basically a division of all the all of the elements of X into groups, okay, into disjoint groups. And so what is in this partition? It's a bunch of subsets, which are all preimages. And they're labeled, each set in the partition is labeled by one image element. So this is a partition of X labeled by points, labeled by the points in the image of F. Okay. Okay, now, so this is basically like an organization scheme, right? It's like a division of the population of X into these subsets, which are just different type categories of different students, right? Different children. They're grouped into categories, and these category, one category is that it's going to this school, school A, and then there's another category of child which goes to school B, right? So we have a partition of the children into these groups, which are non-intersecting. Okay, now I just want to point out a couple of things. So let's notice the following thing. So there is a natural map from X to P. So what does this mean? So the full population is X. X is the whole population of children, and P is the set of schools. It's basically the set of categories which are labeled by schools, right? And there's a natural map, which I'm going to call pi. And what is this map? It takes an element of X and sends it to the set of all elements which are sent to the same thing as X. In other words, it's all the schoolmates, all the classmates of X, right? So how would I obtain that? Well, you could first figure out what is the school that X is being sent to, and then take its preimage. Then you're going to get all the children that go to that same school that X goes to. Okay, so here I'm trying to be as confusing as possible, right? Because I'm using this preimage notation, which is not the inverse of F. Remember, it's just a different piece of notation. F may not have an inverse. You know, it can't be, we can't have a situation where every child goes to a different school, right? The children are grouped together and then sent to school. So yeah, this is like a collapsing map. It's a map that instead of considering, you know, all the children independently, we map them to their category. Sorry, I don't mean category in a technical sense. To their type, you know, to the group that they're in. We say that this child X is in the group F inverse of F of X. Okay. Now, what can we say about this map? What property does this map have? A property that we've seen before.
Surjective.
Yeah, thank you, Yash.
Thank you.
This is a surjective map. Okay.
Sorry, can I just, what effectively you're doing is just sending X back to X right there, right?
No, don't be confused. F inverse does not mean the inverse of F. It cannot possibly mean that because F doesn't have an inverse. F inverse bracket of a point means the preimage. F inverse means what are all the points in X that are sent to F of X.
Right, so it's kind of doing that, but in a different way.
Well, if you have this child goes to a specific school, F of X. But what's in F inverse is all the children that are sent to that school.
Oh, I see, okay.
So it is a subset, and it's an element of the partition.
I have a
So
question.
it's basically sending the student, right, to just the knowledge of their group. So you're forgetting the individual and you're just thinking of the group.
Right,
That's
so
what this map is doing.
If you were to do this on, say, like a function.
It's okay. I don't want to go into any more detail at this
I
moment.
was just trying to see if I understood it though.
It's okay.
Okay.
Try to be as concise as possible. Okay, so the next thing is that there is a natural map from P to the image of F. Okay, this one is very simple. It's taking the preimage F of Y, F inverse of Y, to Y. Okay, so now this is a very simple map because every element of the partition, every subset is labeled by one of these schools. So if I just take that subset to the school that it represents, okay, I'm not really doing much. I'm sending basically the subset to the label, to the school, if you wish. Okay, so what kind of, what property does this map have?
Is
What
this one a
property?
Injective.
Say it again.
Is this one a
Injective.
Diba?
Is this one a bijection?
This one is a bijection. Okay, but instead I'm going to focus on a different map. From P, I'm going to change the codomain to Y. Okay, and the map is going to look exactly the same. I'll take some subset of students, right, which are labeled by the school Y, and I'll send it to Y, which is an element of Y. So it looks exactly the same, right? But I'm just considering it as a different map. Okay, it's a different map with a different codomain. I'm just expanding the notion of the codomain from MF to Y. Okay, what is the property that this map has?
Only injective.
Injective.
Yeah, Lauren, thank you. This is only injective and not necessarily surjective. Okay. Okay, and the last thing I want to note is that if we compose this map, so this one I'll give this a name. This injection, I'll call it J. Okay, and so now what we have, let's just take a look. We have a map from X to P, and we have a map from P to Y. So that means we can compose them. So if we take the map pi, which goes from X to P, and then we take the map J, which goes from P to Y, right? Then what happens if we compose it? Right, we're going to be sending a child, first of all, to its group of classmates, and then we're going to take all those classmates and map them to the school. Right, so if I compose, then it's taking the child and sending it to school. And I can forget about the classmates. Right, if I compose, I'm just going to get X goes to F of X. Okay, that means that the composite is the original map. Okay, and I'm going to introduce a little bit of notation. This is standard notation, but we're not really going to use it that much in class, I think. Maybe it will be useful to do so. When you have a surjective map, you can denote it by having a double arrow. And when you have an injective map, you can denote it by putting a little curl on the tail of the arrow. Okay, and what this means is that F is equal to J pi. We have a factorization of the map F into a surjection followed by an injection. Okay, and this is a general theorem. So we could state the theorem like this, or the proposition: any map F from X to Y may be factorized where pi is surjective and J is injective. Okay, this is just a really simple, just a kind of simple thing to check that you understand how sets and maps and composition of maps works. Okay, so let me draw a picture of this. So let's say that we have, say y looks like this. Let's see. Oops. And say x looks like this. And suppose the map is doing this. Okay, so we can see just by looking at this map. So to check that this is a map, we just have to check that no child is left behind and that there's only one arrow coming out of every object. Okay, and so that's a perfectly good map. Then if I look here, I see that there's convergence of there's collision of values. So this is definitely not injective. And because I have some values that are not taken, this is not surjective. So this is neither surjective or injective. Okay. On the other hand, if I look at the pre-images, I have basically the image consists of 3 points in Y. So the image is just these 3 points. Okay, and so that means that I can produce a partition which is labeled by the points of the image. So that partition will have subset x1, subset x2, and subset x3. Let me just label the points here, 1, 2, and 3. So this means that I have defined a new set P, which has the same number of elements as there are in the image. Okay, these are the points. P is equal to x1, x2, and x3. These are subsets of X, and these subsets are the pre-images. Okay, and then I have pi, the map pi. Okay, the map pi, what does it do? It takes all the points in x1 and sends it here. It takes all the points in x2, sends them here, and takes the point in x3 and sends it here. So here we have a surjective map. Okay. I'm sorry if this strikes you as being pedantic. It's a little bit pedantic, this result, but I'm just trying to make sure that you have crystal clear in your head the way that maps work, okay? And then we have an injection of this into J, which just takes this point to that point. No collisions allowed now. Oops. So let me go from here to here, from here to here, and from here to here. This is J, an injection. Okay. So you can, instead of keeping track of this, all you need to do is keep track of the partition, right? All you need to know is with the partition, and where the partition is sent in the image. Where is it sent and why? And that's enough to reconstruct the map just by composing pi with j. Okay. Okay, now, so any questions about that? The factorization of a map into a surjection and then an injection.
Professor?
Yeah.
I have a question.
Go ahead.
So it does not imply that a map can be factorized in such a way that f is equal to pi of j, such that pi is surjective and j is injective. We can't do it the other way around, right?
Well, you could try thinking about it. Try coming up with an argument. It's a good question that I could put on an assignment. Can you do it in the other way around? Can you take a map, right, and write it instead as an injection followed by a surjection? Think about that.
Okay, thank you.
So Jay had his hand raised and then he lowered it, so I'm not sure.
It's okay. I'm gonna wait. I'm gonna wait until later. I just have a little bit more that I want to get through today, and we can have more questions later. Okay, now. Okay, now I just want to show you something which is going to be very useful as we proceed in this class. But we still have a little bit more of sets to go through. But so I'm just going to kind of show you my hand. So not my hand, I mean my poker hand. So the reason that I'm doing these sets things, these exercises about finite sets, is that when we start dealing with linear algebra of finite dimensional vector spaces, every single thing that we're going to learn about finite sets will have an analog in linear algebra in vector spaces. Okay, and the confusion which arises in the vector spaces is the same as the confusion which arises in the finite sets. So I think it's important that you really understand the way that finite sets and maps between them work. Otherwise, what's going to happen with the vector spaces is going to be even more confusing. Okay, so just to kind of give you a preview of what's coming up, let's talk about a specific finite set. A special finite set, which is the standard set of n elements. Okay. So we're going to call it Bn, B subscript n, and this is just the set containing the numbers, the natural numbers 1, 2, 3 up to n. And if n is 0, then this will just be the empty set. Okay, so I'm defining it here as just the set of the first n numbers. Okay, so in other words, there is a very standard set which has cardinality n. These are not n elephants, these are not n automobiles, okay? They are the first n natural numbers. Okay, so okay, so instead of, I want to show you what you can do with this. And so instead of writing a map from B m to Bn as follows. So now we have an actual subset, now we have an actual set 1, 2, 3, and we have an actual set 1, 2, 3, 4. Okay. And let's say I want to define a map from one to the other, then a typical way would just something like this. I could take 1 and send it to 2, I could send 2 to 1, and I could send 3 to 4. That's a possibility. Okay, so instead of drawing it this way, we can encode it as follows. Okay, so what we're going to do is we're going to build a graph. So as a graph. Okay, I'm going to define the notion of graph more carefully later, but I'm going to use just what you know to be the graph. So in order to draw the graph, we need axes. So we're going to put our axes. Okay, except that I'm going to draw it in a slightly different way from the way that you did it in high school. Usually people put x here and y here, and then you draw points x and f of x. Okay, ordered pairs for x and f of x. Okay, instead what I'm going to do exactly the same. It's just that I'm going to label, I'm going to let the y-axis, I'm going to put it down, going down this way. Okay, so instead of that, I'm going to put f of x going down. X, f of x. Okay. So what's my domain? My domain is, let's say 1, 2, and 3. And my codomain is 1, 2, 3, 4. Okay. And I need to tell you, so let me say this is the domain, and this is the codomain. Okay. And every arrow now needs to be described in this picture. So where does 1 get sent? 1 is sent to 2. So I'm going to put an indication right here that 1 is sent to 2. That's the graph of what the function does to the number 1. It sends it to 2. Is that clear why I put that dot there? This is a discrete map. It only has discretely many inputs and discretely many outputs. So the graph is not going to be a continuous line. It's going to be just a set of dots. Okay, 2 is sent to 1, and 3 is sent to 4. Okay, so what we really have is a 4x3 grid. Okay, I just want you to focus on this 4x3 grid. Okay, 1 is sent to 2, 2 is sent to 1, and 3 is sent to 4. Okay, is any question about this grid and why f is represented by this? So we could call this the representation of f as a kind of grid of points. Any questions about this specific thing? Okay, I guess it's clear enough. Okay, and if we were computer scientists, or if we were computers, then we might want to encode this using a binary grid, right? So this is the same thing as writing a 4x3 grid of numbers, which indicate where the function is. So you could do it like this. You could say 0, 1, 0, 1, 0, 0, 0, 0, 0, and 0, 0, 1. So now we have a 4x3 grid of numbers. Okay, and we could call this the matrix representation of the map F from B3 to B4. Okay? So you see that these maps, so why is it important here? Why is it important that I was using the standard set of n elements? Okay, this is an important point, right? So if I had, n elephants here, and I wanted to just put dots here which represent the n elephants, okay, if I drew this grid, and then if you did the same thing, and if we compared our grids after, they may not look the same. And the reason is because the order of the elephants in the set of elephants is not important, right? So the order that you write down, the order of these 4 points that you write down may not be the same as the order that I chose to write them in the grid pattern, you see? So I'm taking advantage of the fact that there is an order on Bn for all n, and I'm writing them in increasing order like this and like this. That's my convention. That's the way that I set up my system. I could have set it up in a different way, but this is the way that the system works. Okay, because Bn has an ordering, 1, 2, 3 up to n, we're going to label them on the domain axis in the correct order, just like I've done here. So the representation of F as a 4x3 grid, or actually these are called matrices. Okay, so the representation of F as a 4x3 matrix uses the fact that Bn has a preferred ordering. We put the domain and codomain in, sorry, I should write it out, domain and codomain in a specific order on the graph. Okay, if you change the order, right, then the location of the red dot would be different, right? Because 3 is sent to 4, but if we had, if we didn't label these, and if this one was listed first, then the red dot would appear up here instead of down here, and the position of these ones would look different if I reordered the codomain. If I reordered the domain, the columns would switch around. Okay, so let me just write that. So note, if we permute the codomain, okay, then the rows would permute. This would, so let me just draw it a little bit more with fewer words. So if you permute the codomain, this gives a permutation of the rows. And if you permute the domain, this gives a permutation of the columns. Okay? Okay. If you permute the domain, then of course, what appears in these columns would be permuted as well, because they are only representing where the domain is being sent. Okay? So the concept that I wanted to explain on this slide is that there is a nice way of writing maps between sets where the sets are the standard set of n elements. When it's the standard set of n elements and the standard set of m elements, and we have a map from one to the other, then we can put the domain and the codomain in a particular order, in the natural order, and we can write 1s and 0s to indicate where the domain points are sent in the codomain. And then this matrix completely encodes the information of the map. Okay. Any questions about this fact, about this point of view?
I have a question.
Go ahead.
So this is really only useful if it's the standard set of n elements, right? Like if there was a random, like if it was just 1, 2, 4, 5, right? Like if that was one of the sets, then then this grid wouldn't work, right?
Yeah, then you would have to be more careful, and you would have to label the domain in the way that then you'd have to kind of keep track of what your domain and codomain elements really are, and not just have a 4x3 grid of numbers.
Right.
In order to interpret properly this grid of numbers, of binary numbers,
Right.
you need to be in the system that we agreed upon, that
Right.
we have a domain which is B3 and the codomain B4.
Okay. Thank you.
When you mentioned that everything in the set theory has an analog in linear algebra, is the analog to the idea
Don't
that
ask about what the analogs are, because we will see what the analogs are when we cover that material. Yeah, it's like reading the end of a book before you read the beginning. I never do that. Okay, anything else?
This might be a rudimentary question, but what do you mean by standard set?
So what I mean is literally this set, right? So if you ask me the question, give me a set of cardinality n. I could give you many answers, right? I could give you n desks, I could give you n students, n children, whatever. But there's a standard answer that I could give you, which is the set Bn, which I just defined there.
I see. Thank you.
Okay. You could just take it as a definition. That's what it is. I defined it today in this class. The standard set of n elements is the first n natural numbers. Okay.
Hello, Professor.
Yes, go ahead.
I have a question. What means the order? So what means the order in this kind of condition?
I'm talking about the order 1, 2, 3. They occur in the natural order, 1 before 2, before 3, so that when you draw this diagram, you have to label the points on the domain in order. So the point 1 is here, and then the point 2, and then the point 3.
Oh, I understand.
If the domain consisted of people, you would not know which order to put them in. But because the domain is a set of natural numbers, you know which order to put them in, because they have the order of the numbers.
Okay, thank you.
Okay. Okay, the last thing I want to do today is explain exactly what a graph is. So to define what a graph is, we need a new method for constructing sets, which is the Cartesian product. Okay, and this is another kind of important structure that occurs all over mathematics. So if we given sets x and y, their Cartesian product which normally is just called their product. It has the notation x cross y, like a little multiplication times, but it's really the Cartesian product, is defined as follows. Okay, x cross y is the set like this, okay? And this is a new notation. This is an ordered pair. So this is not a set, it's an ordered pair. So that means that so x, for example, if I put 1, 2, this is not equal to 2, 1. Okay, whereas 1, 2, the set 1, 2 is equal to the set 2, 1, because sets don't care about the order of the elements. But when you have a parenthesis, when you have a smooth bracket, right, then order matters, and you must separate the elements with commas. Okay, and they occur in a particular order on the page. Okay, so these are, the Cartesian product is the set of ordered pairs, x, y, where x is taken from the first set and y is taken from the second set. So for example, if P is equal to RGB, okay, and we take, so then B2 cross P would be the set of ordered pairs 1R, 2R, 1G, 2G, and then 1B and 2B. Okay, so it's a set containing 6 ordered pairs. Okay, and similarly, if we have K sets, then we can take their product, x1 cross x2 cross all of them up to xk, and this would be the set x1 xk, such that xi is in xi for all I. Okay, and this is called a k-tuple. Okay, or list of length k. Ordered pairs are very short lists. It's a list of length 2. Okay, and this can also be written in shorthand. This is just notation. The shorthand notation for this is the product I equals 1 to k. It's a big product of xi. And a special case is that if you take the same set and you product it with itself k times, this has a special notation, which is x to the k. Okay, so I just wanted to introduce the Cartesian product. The Cartesian product is all about lists, lists as opposed to sets or tuples. Okay, lists and tuples are the same thing. They look like sets, but the order is important, and so you must be careful to list them in the proper order. Okay, and so finally, I can define the graph of a map f from x to y is the subset x, y inside x cross y. It's all the ordered pairs in the product of x and y such that y is equal to f of x. So if this is x and this is y, then we have a bunch of ordered pairs, x1, x2, x3. This is x. This is the ordered pair x3, f of x3, x2, f of x2, and so on. So there are many points in the Cartesian product. Okay, there's many points in here, but there's a special subset, the red subset, which consists of the points satisfying this relationship that y is equal to f of x. The second element is equal to the function or the map applied to the first element. And so this is by definition the graph. We usually have a notation for this. You could just call it the graph of f, or you could call it gamma sub f, because graph, well, gamma is the Greek letter G. Okay, so so now we have the Cartesian product, and we have and you know, the Cartesian product can give you lots of other sets. You can take products and produce gigantic sets using it. Okay, that's all I wanted to talk about today. I'll leave it there, and I'll stick around because today is my office hour. So I'll just stay on, and we can just have questions. So let's just follow the usual format. So if you could write your question out, and then Syed will call on you. Oh, sorry, Syed, are you okay with this hour?
Yep.
Okay, thank you. So yeah, so just go through that process, and then I'll try to get to as many questions as possible.
Okay, so Neil has his hand raised.
Hi.
Hi,
I'm just
go
wondering.
ahead.
So this is a pretty interesting interpretation of 2D graphs, but is there a similar way to do it for like 3-dimensional, where you have triplets as your points that you're graphing? Where you combine
So well, okay, so the reason why 2 dimensions is occurring here, like the reason that my picture is 2-dimensional, is just because a map has a domain and a codomain. Okay, so I divide the domain on one axis and the codomain on the other axis. We don't know what the domain and the codomain are. They could be anything. They could be 100-dimensional spaces.
Right, right.
Okay, but I'm just drawing here like a cartoon picture of the domain and the codomain as if they were lines. Okay, and whenever we're dealing with finite sets, then of course we can just always do that. Now, you know, when would you draw a 3-dimensional cartoon picture? That would happen when more than you know, where you had a kind of an occurrence of 3 sets. Let's say, I mean, you know, you could consider a map. You could consider a map which goes from x1 cross x2 to y. And then you could say that
if the Cartesian product is your input, then you would have all the ordered pairs just in your domain of sorts.
yeah, I mean, you could still draw a 2-dimensional picture by putting x1 cross x2 as your domain. Or if you wish, you could just increase the dimension just for visualization purposes. And then this would be your domain.
Mm-hmm.
And then you would draw, you know, the graph above that domain. Okay, so here the fact that I have a 2-dimensional picture has nothing to do with the page or a visualization or anything. It just has to do with the fact that we have a domain and a codomain. Those could be anything.
I guess, yeah, I was thinking maybe another analog would be some sort of map-like structure that actually takes 2 input sets and maps to 1 or something like that.
Yes,
Then,
that's right. Yeah, yeah.
But I'm
So you could you could have a different type of thing, but you could have a different type of relation between 3 sets, but yeah, I don't really have anything interesting to say about that. Okay, anything else? Let's go to the next.
Okay, so Dixshant has a question.
Yeah, go ahead.
Hi, I just wanted to clarify some things about the tuple that you said earlier about x1 cross x2 and the number of tuples it gives you. So first you'll do like the first element of x1 and then the first element of x2. Then another tuple would be the second element of x1 and the first element of x2. And then you keep on going and then you have those permutations. But if you have, let's say in higher dimensions, if you have x1, x2, and x3, would it like, is there like a way to find out like the permutation, a way to derive the formula for how many?
There's not, okay. There's no permutations here happening, right? I'm taking, anything goes in the first slot, anything in X can go in the first slot, and anything in Y can go into the second slot. Okay, so there's no question of permutations here. Keep in mind that you cannot put an element of Y in the first slot. You can only put it in the second slot. Okay, so what you are driving at, what you're getting to, is you're trying to figure out what is the cardinality of a Cartesian product. If I know the cardinality of X and I know the cardinality of Y, can I figure out, can I count the cardinality of X cross Y? And you indeed can, and you should do it, but don't do it right now. Okay, next.
All right, so Lauren has a question.
Yeah, Professor.
Hi.
Hi. The operation of Cartesian product is not commutative, right?
That's right.
Okay, thank you. That's all.
Okay, so Shivraj has a question.
Yes, sir. I just wanted to ask, why did you write list of blank 2 instead of list of blank 1?
It's because there's 2 elements in the list.
Okay, so whenever we're writing the length, it should be the list of the number of elements.
Yeah.
All right, thank you.
Okay, so Charlie is next.
I just had a question about like the way you notated like the x1 cross x2 cross all the way up to cross xk.
Oh, yeah, okay.
Sorry, so what is it? It says I is equal to 1, or is I is equal to something else?
It says I is equal to 1.
Okay.
Okay, so this means that you're taking, excuse me, it's saying that you take the product of the xi's where the I ranges from 1 to k. That's what the meaning of this is.
Oh, I thought that was an h. Okay, that makes a lot more sense. All right, thanks.
All right, so Neil, you have a question?
One other thing, just to clarify, it does seem like you need to have both sets have the same cardinality in order to perform the Cartesian product.
Why?
I guess I was just thinking in the case of, like if you had more elements in one than the other, like say 5 elements in one and 3
What about
elements.
if we had 3 elements in one and 2 elements in the other?
Right, so okay, so elements just have to be repeated in some cases too.
So, you know, what is in the Cartesian product is a list of 2 things. So each element of the Cartesian product is a list of 2 elements, one taken from the first set and the other taken from the second set. Any element can be chosen for each slot.
Okay.
So there's 2 possibilities for the first element and there's 3 possibilities for the second element in this case. And so there would be 6 possibilities in total, because you have 2 independent choices.
And in general, can you, it seems like there is, I mean, I would assume there's at least some definition for like a triple Cartesian product, you know, where you simply make a triple out of 3 sets.
Yeah, but
Is there a
look,
way to expand that? Is there like an infinite dimensional Cartesian product where if you add like
I
an
mean,
infinite number of intervals, then you can find the Cartesian product of all of them in some way?
yeah, so you notice here that if you have k sets, you can take the product of all k of them,
Mhm.
and you get lists of length k as the elements of your Cartesian product.
Right.
So yeah, indeed, you can take products of many sets. You can even take infinite products.
And then you just have like an infinite tuple as your elements.
Yeah, a list, an infinite list, sometimes called a sequence.
Wow, cool. Thank you.
You're welcome.
Okay, so Michael has a question.
Can we say that a function is equal to its graph, besides the fact that the domain and the codomain need to be specified?
Well, when you have a graph, the domain and the codomain have to be specified, because the graph is a subset of the Cartesian product of the domain with the codomain.
Well, if you have a graph, wouldn't only the image be specified?
No, because you need, I don't know what you mean. I mean, you need, the graph is a subset of x cross y. So
Right.
if you are to tell me a graph, you need to first give me x and y, then I can take the Cartesian product, and then you have to specify a subset of that.
I'm saying so just the, I thought so the graph is just the x and y coordinates, But let's say, so if the map is not surjective, then the graph of the function is not going to tell you all the elements in Y, right?
Correct. But
So
like I'm saying again, the graph is not just this set of red dots. If it was just the set of red dots, I could just take my red dots, rip them out of the page, and just put them on the floor. And what would that tell you about the function? It wouldn't tell you anything. The purpose of the graph is that it's the positioning of that set inside the Cartesian product. It's the precise positioning of it which tells you what the function is.
Okay, I see.
So if you don't know where the graph is sitting, if you don't know that it's in X cross Y, you wouldn't be able to tell that the map is a map from X to Y.
I see.
Okay, now to answer your question more generally, the graph is equivalent information to the map. So if I give you the Cartesian product and I specify the subset, which is the graph, that's exactly the same information as specifying the map. Okay, and in fact, if you really think about it, if we go way back to the beginning, I said back here in the definition of map, where is it? A map, a map from set X to set Y assigns to each element in the domain an element in the codomain, right?
Right.
So here, if you pay attention, or if you look a little bit deeper, you'll see that I'm kind of, I'm using natural language, I'm using human language to explain what a map is. I'm saying that it assigns, it's like a machine that eats the input and gives you an output, right? I'm trying to give you an intuition for what the map is. Right? It just takes every element in the domain and sends it somewhere. But if you really wanted to rigorously define what a map is, you could do it using the graph. You would say, what is a map from X to Y? Well, it's the following. You take X and Y, you take their Cartesian product, that's a new set.
Right.
And then you specify a subset of that. And the subset has to have a certain property that above every element of the domain, you have to have a unique element of the codomain in the subset. So that way it's really telling you for every possible X, it's giving you a specific value above that in the graph. So as long as you give me a subset satisfying that condition, you could consider that to be the definition of a map. Okay.
I see. So I could just do, say, like F is equal to like a 3-tuple, like the domain, range, and then the set of, in this case, would be the red dots, basically.
Correct.
Thank you.
Okay, so Kanav has a question.
Hi. So going back to when we were talking about partitions, so the partition, it's a partition of X, which means it is a subset of X, right?
No. What's a partition?
It's the preimage.
So here's X, right?
Right.
X is the red set. It contains how many points?
5.
Okay, so what's the partition?
X1, X2, and X3.
Yeah, so what are the elements of the partition? Like X1 is an element in the partition. So what is X1?
X1 is it's the preimage, right?
Well, I'm not talking about the map. I'm talking just about the partition. So you said that X1, X2, and X3 produce the partition.
Right.
So what is X1? What is it?
It's an element?
No. Well, okay. I mean, everything could be an element, but it's X1 is a subset of X.
Right.
And X2 is a subset, and X3 is a subset. So the partition consists of 3 things: X1, X2, and X3. And each thing is a subset of X. So the partition consists of 3 subsets of X. That is what the partition consists of.
And the partition itself is also a set, right?
Correct. The partition is a set of things. These things are subsets. So it is a set of subsets of X.
But if everything is everything in the partition is a subset, wouldn't that make it also a subset? Like,
wouldn't that make the partition a subset?
Right, because
well, okay, so you're saying that X1, sorry, the partition, so the partition is the set X1, X2, X3. That's the partition. It is a set of things, and each thing inside here, this is a subset of X.
Oh, so we don't consider what's actually inside the subsets, right? It's just the elements themselves, but that's not actually inside X.
You're in a transitional state of nonsense and sense. Just keep thinking and then come back.
Yeah. All right. Thank you.
Okay, so Dikshant has a question.
Yeah, hi. I have a question about the similar thing. So, when you talked about these partitions and you talked about the pi and j, I couldn't really follow what the implication was of going through this entire thing and how this related to the grid. Like later on, you drew a matrix grid to show how the function maps to the grid, but I couldn't quite see the clear connection between how having this showing the the partition related to showing us towards like how did that help us in formulating the grid?
Oh, it's not. It's a different topic. Yeah. So here, I what have I done here? So we started talking about maps, and we started talking about properties of maps, and then here we have a result. The main result of this section on maps is that any map can be factorized into a surjection and an injection. So I'm done now with the properties of maps, and I just moved on to looking at another another way of thinking about maps. So it's just it's a different section. So this is like you could call this section as the kind of the explicit description of maps. That's what I'm trying to explain here. These will be the analogs of matrices later on. So later on, we're going to study linear maps, and these linear maps it'll be possible to explicitly describe them numerically, let's say, using matrices of numbers. But you see here that I wanted to make a distinction between the abstract description of maps and what they really are, and then the explicit description in terms of numbers. Those are different things.
As a side question, when we do all these things in class, in lecture, I was wondering where can we find, like other than the assignments, if we want to find practice questions to which we can check the answers ourselves and see all the stuff. Can you lead us to a resource where we can do such practice questions?
Well, okay. I mean, I'm doing a preliminary section on sets and maps and stuff. And this is before we start the textbook. I mean, we're going to get into the textbook very soon, within 1 or 2 weeks, and then you're going to have plenty of problems. So right now we're just in a temporary phase where it's about sets. And now, I don't want to make you go read books on set theory. That doesn't make any sense. So at the moment, I don't have extra questions, but you can, I would recommend reading things like Wikipedia pages on these topics. I would recommend, just playing with them on your own. Believe me, you're not going to have too much time without enough problems. Right now, we're in an easy phase of the first 2 weeks of class. Eventually, it's going to get much more based on the textbook, and you'll have plenty of problems.
Thank you.
You should also take the homework questions and try to improvise on the theme of the homework questions and make other questions. Let me just see, how many people are here right now? Let me check.
104.
104? So we're in office hours. Let me try something. Just want to try. Okay, next question.
Okay, so Deba has a question.
Yes. So my question is about how, so we can take any bijection and decompose it into an injection and a surjection, but can we go the other way? So can we compose a surjection and an injection and always get a bijection?
Sorry, I don't understand how that is the other way of the first thing you said. They seem to be just different. Maybe just phrase your question as a single question. And
Okay.
I'll try to tackle it.
Pardon?
I'll try to understand. I'll try to understand it again. Just try to ask one question. Don't
Yep.
compare it with.
Can you compose any injection and surjection, assuming all of the domains and codomains line up, and get a bijection always?
Okay, but try it.
I don't think
These questions. See, I mean, these are good. I mean, it's good that you asked this question, because then I can tell you that you shouldn't have asked it. You know, so the idea is there's no need to ask people about these things, because you could just try the first thing that comes to your mind, right? So what's the easiest injection you can imagine?
1-to-1, like one element.
1 point being injected into what?
Just one other point.
Okay, that's a simple one, but make it a little bit more complicated. How would you get a slightly more complicated injection? 1 point going to what?
Going to 1 point, and then a second point going to a unique other point.
No, there's no and then. I want one injection. So start with 1 point. I'm going to inject it into. So this is a set containing 1 point, right? Let me do it like this. B1. It's a set containing the number 1. I'm going to inject it into B2. 1, 2.
Are you
Sorry,
writing?
Marco, to interrupt. I don't think we can see what you're writing.
Okay.
There you go.
So you agree that this is an injection? It takes 1 to 1.
Oh, okay, yes.
Okay, give me an example of a simple surjection. Surjection to what?
To another set with one element.
Okay, so let me take B1.
Mhm.
And what should be the map? 1 goes to, and 2 goes to, what should 1 go to?
1. And 2 also to 1.
Okay, and then if we compose, what do we get?
I think it is a no, it's not, because both.
1 goes to.
Oh, yeah, okay.
1 goes to 1 and 1 goes to 1. So we have 1 mapping to 1. So that's a bijection.
And we don't care about the second element of B2.
There is no second element.
Of B2?
But I'm trying to compose. I'm supposed to get a map from B1 to B1.
Yeah.
So there's only 1 element that I have to apply.
But I guess my point is, like, when we have the intermediary.
The composition is a map from here to here. Do you agree?
Okay. Yeah.
So then the composition has domain B1 and codomain B1. So there's no, who cares about B2? B2 is irrelevant.
Okay, but this happens here, but does it always happen?
Well, so suppose that you wanted to give me, is this the only possible surjection? Is it only possible to surject onto B1? Or can we have something else here as a surjection?
No, you can have something else.
What, for example?
Like B2 even.
Okay, so let's put B2. And what should the map be?
It can be 1 to 1 and 2 to 2.
Yes.
Or it can be the same it was before.
And then what would be the composite? Is the composite going to be a bijection?
No.
No, you don't even have to compute it.
Yeah.
Because the domain and the codomain have different cardinality.
Because that element 1 in B1 under the composition is getting mapped to 2 in B2 at the end.
Wrong. 1 is being sent to
1.
1 is being sent to 1 and 1 is being sent to 1. So 1 is sent to 1.
Okay. But then we do care that the 2 from B2 is also sent to the.
So again, you care too much about this B2 person.
Okay.
We're composing.
Okay.
When we compose, the middle guy is eliminated.
Okay.
Right? It's like cutting out the middleman.
Okay.
Who cares about what profit the middleman has or had or didn't have? It's irrelevant. This is the domain and this is the codomain. So where does one get sent? To
It's
one.
one, but it's not a surjection anymore because we have.
Because there's there's no other element. There's no possibility of hitting hitting.
Okay.
Okay.
We got there. Thank you.
You're welcome.
All right, so G-Cow has a question.
Hi, Professor.
Hi.
Hi. So my question is, for all the terminology of a map, does a graph or matrix has a corresponding terminology? So for example, we have surjectivity for a map. So can we say a graph is surjective, or there's a different name for that?
So the graph is the equivalent information to the map. Okay, the graph is equivalent data to the map. So you can figure out what is it about a graph that makes the map surjective. How would I think about that from the point of view of a graph?
Okay.
How would, what would the property of the graph be so that the map would be injective or bijective?
Well, if you draw a line, if you fix a point on Y, then you can.
I don't want to hear it now. You should think about it. I'm just saying that it's a good idea to think about it because the map and the graph are equivalent data. So anything that we know about maps, we should be able to tell them about the matrices.
Yes, yes. My second question.
We're going to do more of that next week.
Okay. My second question is that now we understand a map can always be decomposed. So is graph and matrix. And we also know that matrix multiplication can be optimized.
We haven't talked about matrix multiplication, so I'm not going to talk about it.
Oh, okay. I was just wondering if we talk more about the question transformation between the three type of the concept.
What is coming up in the future, we don't know.
Okay.
We don't know what's in the future. Only the syllabus can tell us. I appreciate your enthusiasm and eagerness to know about the future, but you have to, in meditation, you learn how to live in the present. You have to learn what is in front of you. What I have found is that the people who are very concerned about the future, they tend not to learn what is being given at the present. And in the end, you're gonna be behind. If you can't raise your hand, I don't know why you wouldn't be able to raise your hand.
Yeah.
You could ask in the chat if you can't raise your hand. Oh, I guess you could even raise your hand in person.
So Anatoly has a question.
Yeah, hi. When you were describing the factorization of any map F into a surjection and an injection, you introduced these maps pi and j, and you said that they're natural maps. What do you mean by natural in that case?
What I mean is that they don't involve any kind of choices. They are, that I can define them without any additional data. That the data is specified, like for example here, you see that, yeah, here it is. So if, I have a map F, and out of this map, I created a whole bunch of stuff without any additional data. I created the image subset, I created a partition of X, and both of these structures, I extracted them out of the map F without any additional given data. And then not only that, but I even have a map which I can extract from that same data. There's a map from X to the partition that I extracted from the map.
I see.
So that's what I mean, that all of this is a mathematical consequence of having a map from X to Y.
Right. Okay. Yeah, that makes sense. Thank you.
Okay, wait, I'm gonna send, I'm sending people a list. Oh yeah, yeah, okay, wait. How do I get this link? Okay. Okay, so I just want people to test this out. So go to this site and make an account. And it will only work if you have utoronto.ca email account. And once you've made an account, enroll in the MAT240 subclass in there. And it has a code, which I just put in the chat. Okay, next question.
All right, so Omar has a question.
Okay, go ahead.
Yeah, so my question is just like a bit of like, I just need a bit of clarity on the graph. So the graph's definition is that it's a representation of the subset of a subset of X.
So, sorry, you're asking about the graph?
Of the product of X and Y, right?
Sorry, you're asking about what the graph is?
Yeah, so the graph's definition is that it's a subset of the product of X and Y.
Yeah, correct.
Right. So why do we say subset if it's just a representation of the points? Couldn't we say they're equal? That the graph is equal to the product of X and Y?
So, okay, so if the domain here is R and the codomain is R, right? I can have a map from R to R, which is X goes to X squared. The graph is this subset. This is the graph of F. Okay, it is a subset of R cross R. It is a subset of the ordered pairs input output.
Yeah.
Every element of this subset is a list, which lists first the input and second the list in the list is the output. So it's input output pairs. And of course, given the input, the output should be determined, should be unique. You know, once the input is specified, the output should be automatically given. So that means that you cannot have all possible ordered pairs. You know, once you fix X, the second element of the list must be F of X. It can't be anything else. So it's only a subset. It's a proper subset of the Cartesian product.
Proper subset? Wouldn't it? It can be possible that they're equal though, in some cases.
Well,
if it's X to X, for example, or no?
No, that would, of course, you're comparing this subset of this space. The product is all possible ordered pairs. So it's the plane.
Sorry. Yeah, okay, now I get it. Yeah, thank you.
Named after René Descartes, who invented the idea of graphing functions.
I see. Thank you.
Okay, so Sung has a question.
When are the lecture notes going to be uploaded? Because I can't find them on Quarkus.
I'll put them on the web page, but they're not up yet.
Okay.
Okay, so Qin Yuan has a
Okay,
question.
I'm just curious whether this thing worked. Let me see. Yeah, if you can get to the quiz, just do the quiz, and it's not an actual quiz. I'm just testing whether this software works. There isn't really any good software available for doing in-class testing. This one is a it's a free software that was developed by a professor at Queen's. I'm just testing it out to see if it can be used. Did anyone complete the test? It worked.
Yes, I did.
Okay, good. I'll check it out after to see what the results are, but it's not important.
Yeah, it worked.
Any more questions?
Yeah, Qin Yuan has a question.
Oh, okay. Hi, Professor.
Hi.
I have a question about. Oh, sorry. I have a question about the Cartesian products.
Yeah.
The special case under the node.
Yeah.
I don't fully understand that one. The x products and there's the letter k above. I don't understand that equation.
This is just the definition of this notation. This is a notation
yeah.
for the product of k copies of one set. So if you have a single set and you just take multiple copies of it and you take Cartesian product of them, okay, then there's a shorthand notation for it, which is x to the power k. Okay, so this is used all the time. For example, in this case, so in this case, the product R cross R of the domain cross the codomain, this is otherwise known as R2.
Oh.
Okay, it's just a notation. This is notation for this concept.
I see. So what does that like R2 actually mean here?
It means this, R cross R. It means that you take two copies of R and you take their Cartesian product.
Oh, just like the result of
R3
the Cartesian
is by
product.
definition R cross R cross R.
Yeah. Oh, I see. Just like a result of the Cartesian product of two sets, right?
Yeah.
Oh, I see. And I have another small question about the graph. So the graph we have, it is just like a piece of mapping of the whole mapping. Is that correct? I'm not sure if my question is clear.
No, try again.
Yeah, well, I mean, so like the graph we have here,
Yes.
it is just a piece of a graph of the whole function or map.
Okay, so here I've drawn a picture of a plane R cross R. Okay.
Yeah. Yeah.
So this is, let's say, 3, and this is 4, and this point is the point 3, 4. It's a list of 2 elements, 3 and 4. Okay. Yeah. And the set of all possible 2-element lists makes up the entire plane.
Yeah.
Now, inside that plane, we have a green curve, a special subset. This subset is called the graph of the map F. Okay, yes. This map takes a point in the domain and sends it to a specific value, the value being the square of that point.
Oh.
So what I do is I take, well, this is not a very good diagram at this point, but, oops, sorry. So for example, here I have 1, f of 1 is 1. So the point 1, 1 is in the graph.
Yes.
2, 2, 4 is in the graph.
Yes.
Right. So the graph is a subset of the Cartesian product of the domain and the codomain. It's a subset of R2.
Yeah, I got it. Thank you.
Okay. Dixchant has a question.
Yeah, hi. I just had another conceptual question about surjective graphs. So when we see the graph is surjective, right? So it means that
a
map
is surjective.
Okay, so a map is surjective, but I've heard the term a surjective function. Can a surjective map be a function as well? Because
function is just function and map are interchangeable words. But a lot of people prefer to use function when the map takes numerical values. Okay, so normally the functions that you learned about, like polynomial functions, they have numerical values. Okay, but so it's often called functions. Functions and maps are basically the same thing. It's just more common in modern usage to call them maps. Maps between sets, maps between groups.
Okay. On top of like that, that's my question. So when we say it's a surjective, let's say a map or a function, it means that it is possible for one element in the domain to go to sorry, it's possible for two elements in the domain to go to one element in the codomain, right? So let's say
No, that has nothing to do with surjectivity. Surjectivity has to do with the fact that you cover everything in the codomain, that all possible values are taken. Sur, it means, you know, in French, sur means on top of.
Yeah.
Surjective. It means that you're throwing a blanket on top of the, you're throwing a tablecloth on the table. You're covering the entire table.
Right.
So in order to be surjective, every possible value must be taken.
Right. So along with that, it is also possible in a surjective map for two elements in the domain to go to one element in the
Yes, that's possible.
codomain.
Yeah, it's possible.
So when that happens, that is no longer a function, right? It just becomes a surjective.
Wrong.
Because then it violates the vertical line test. Because then
if two children go to the same school, right, that's not a problem. There's plenty of children that go to the same school. The map from children to schools is just sending each child to their school. There's many children in one school. That's not a problem for mapping.
But if you look at the same thing with functions and numerical values now, in high school,
functions are maps. You don't believe me, but it's true. There's no difference.
So that is true, but in high school we were taught that for it to be a function, it must pass the vertical line test, and that
The vertical line test. Yeah, that's right. You were taught the right thing.
Yeah. So if we have
vertical line test, what does it mean? It means that every input is sent somewhere. It's not sent to 2 or 3 different places. You're not taking the child and chopping it up into pieces and sending each piece to a school. That's not a map. The vertical line test means that the child is sent to a specific school, not to 3 schools.
Yeah, I think it's clarified now. Yeah, I had a confusion. Yeah. Okay. Thank you.
Okay, so Jay has a question.
So someone had mentioned 3-dimensional space earlier, and I had a question about relating that back to the Cartesian product. So if we have the Cartesian product, which is shown on the screen right here, between the sets of all real numbers, and you get r squared. So that's essentially this plane, right?
Yeah,
we have this flat plane. So if we take the Cartesian product of that plane with, I guess you could say, the set of real numbers again, you would get your infinite 3-dimensional, like either you call it a, is that correct? Is that the correct interpretation?
Yeah, correct. You would get R3, yeah.
Okay, and then for any nth dimensional, okay.
Yeah, you can just keep taking Cartesian products and you'll get lists with many, many, many entries, and the dimension will go up higher and higher.
Okay.
Okay, so Nadia has a question.
Hello,
Hi.
Professor. I just wanted to ask, how much of our grade will participation be, like in class, and if there is any other participation, like quizzes is participation, but apart from that, is there anything?
So did you look at the syllabus?
Yeah, I did.
So you must have seen that there's 85% on
Yeah.
assignments and 15% on in-class quizzes.
Yeah.
Yeah, that's it.
We just participate in the in-class quizzes and that's it.
Yeah.
Okay. Okay. Thank you.
Good luck if you do that, though.
Okay.
All right, so it doesn't look like anyone else has their hand raised or any questions in the chat. Oh, I guess
It's office hours, so you can ask things about the assignment or how to. Warning to everyone, make sure that you upload the assignment with plenty of time to spare, because there's always a couple of people who decide at 11:59 to submit their assignment, and then they miraculously get their computer plug gets knocked out, and then they lose power or something, and then they come and they email me and say that they submitted their assignment 1 minute after the deadline, and surely that's okay. I mean, no, it's not okay. So just be careful. You have plenty of time. You could start the assignment now and you'd be perfectly okay.
Okay, so Kinwan has a question.
Yeah, hi, Professor. I have one last question about notation. In the partition, that part, the x to the map from x to p is pi. So that notation is not has not a different meaning from the pi Wienerling circle, right? I'm not sure about that. So.
Oh yeah. Yeah, it has nothing to do with the number pi. Yes.
So can we just use another number or letter to just replace it? And just
no, I'm keeping pi.
Okay, so we can, but just it's you like to use pi to represent that mapping, right?
The reason that pi is the often used for this map is that pi is the Greek letter for p, and this map is otherwise known as a projection map.
Yeah, I see.
The projection map, and the word projection starts with p, and pi is the Greek letter p, and that's the reason.
Okay.
That's the reason. Yeah.
Okay, thank you, thank you.
It's called a projection map because you are basically reducing the information. You're projecting out unnecessary details. You're saying, I don't care what the children are. I only care what school they go to. So I'm going to project the set of children to the set of schools. And then when you do that, yeah, you're projecting out all of the individuality of the children. You're only considering the school group, the group of school children.
Oh yeah, so we're just caring about the subsets in
the subset. Yeah, which subset are they?
Yeah.
You look at the individuality of the children. Yeah.
Okay, I got it. Thank you.
Okay, so Deba has a question.
Just on the problem set, I just remembered, I'm looking at question 3, part C, which says prove that F is invertible, i.e. it has an inverse if and only if it is a bijection. And I just want to clarify, we have to prove this both ways.
Yeah, so this is something you need to get up to speed on right away. And that's the meaning of if and only if. So, you know, if and only if means that the implication, the logical implication, goes in both directions.
Mm-hmm.
Okay, so A is true if B is true, means that B implies A.
Mm-hmm.
Right? Okay. And A is true only if B is true, means that A, if A is true, it must be that B is true. Mm-hmm. So it implies in the forward direction that A implies B. Mm-hmm. So the if statement implies B implies A, and the only if means that A implies B. So if and only if is something that you'll see at least 10 times a day during your undergraduate career. And if and only if B. Okay, the if means that B implies A, and the only if means that A implies B. So this is true. This is equivalent to A implies B and B implies A. So someone mentioned that it was explained yesterday in MAT240.
Yes. So this part I follow. So there is 2 parts to the proof here. One that shows each way of B implies A and then A implies B.
Yeah, correct.
That's what I want to clarify.
Okay, so Dikshant has a question.
Yeah, so this question is like, I think we covered this in the second lecture or something, when you're talking about bijections, and you gave an example of 1, 2, 3 being like a bijection from 1, 2, 3 to itself. And then you talked about an inverse in that bijection, something about I don't know if I heard you right, but when I'm looking through my lecture notes, it says that each function, each bijection inside the set of bijections from 1, 2, 3 to itself, the inverse is inside that set itself.
No.
Is that correct?
So here we have a bijection. So this is the domain, this is the codomain, right? And what is a bijection? It's just a map from here to here, which satisfies some property. So I listed all the possible bijections.
Mm-hmm.
So the set of bijections has how many elements in this case?
6.
Yeah, each element is a bijection, right?
Mm-hmm.
So let's take a look at this element here. This is a map that takes 1 to 3, 2 to 1, and 3 to 2. What would be the inverse of this map?
The one right next to that, on the left.
Yeah. So this is the inverse of this map, right?
Yeah.
So that means that the inverse of this bijection is another bijection.
Oh, isn't that like obvious? Okay, I find.
Yeah.
Yeah. Okay. Okay. Yeah. So it doesn't have to be that if there's a set of so if there's one set and then you make a bijection from that set to itself, it doesn't have to mean that each element in that set of bijections will have an inverse which belongs to that same set. It could be like, for example, the second element.
You have a bijection and it has an inverse. Is the inverse a bijection?
Yeah.
So you think that's obvious?
Yeah, because if it has an inverse, that means when you compose the two things, it has to give you.
I'm going to stop you there. So in the assignment, it asks you to prove that a bijection is the same as an invertible map, right? So if F has an inverse, then that inverse has an inverse because F will be the inverse of the inverse, right? So it's always true that if you have a bijection, then its inverse will be another bijection. So the set of bijections, right, is closed under inverse. So if you take one bijection and invert it, you're going to get another bijection.
Yeah. Okay.
So yeah. I think you were, it may not be what you intended to say, but what you said was that if you take the set of bijections, it's not necessarily the case that the inverse of one of those bijections is in that set. But it is, because it is a bijection, so it's in that set.
No, because like if you look at the same set over here, the second element, the inverse of 1 goes to 1, 2 goes to 3, and 3 goes to 2. It's not in this entire set, right?
Oh, where is it?
Well, because the inverse of this would be, so 1 goes to 1, and then 1 has to go to 1 again, and then 2 goes to 3, 3 goes to 2, and so it'll be.
Okay, so is there a map here that sends 1 to 1, 2 to 2 to 3, and 3 to 2?
No.
No. Why? Okay, I'm going to stop your question here. Think. The answer is staring you in the face. Okay, more questions.
Yeah, so Bhavjot had a question in the chat. If you want to unmute yourself. Yeah.
Is the difference between a pre-image and an inverse is that an inverse is a function and a pre-image is a subset? Well, I mean, it's like saying, what's the difference between, a desk and the United States of America? I mean, they're different. What do you want me to say? What you said is true. That is one of the ways in which they're different. The inverse is a function or a map. The other thing you could say is that pre-images of elements always exist. Inverses of maps don't always exist. See, this is a type of question that artificial intelligence wouldn't really know how to answer at this point. But I'm a human, so I can answer it. It's a category error. There is no answer. Yes. You're welcome.
All right. So Dehan has a question. Dehan?
Am I audible?
Yeah.
Yeah, hi, Professor. I had a question about the definition of the group SX from the second lecture.
Yeah.
So you said that the operation of composition kind of formed a an associative multiplication. What did you mean by that?
I just mean this. Composition is associative.
Yeah, but I mean the word multiplication. That's where I'm confused at.
Right. Okay, so so a binary operation on a set X, okay, what is it?
It takes two elements and produces a third.
Yeah, it is a map from X cross X to X.
Yeah.
Okay, it takes an ordered pair A, B, and sends it to, let's say, I mean, you should write it in general as MAB. Okay, but for example, it's typical that we could use some, whenever we have a binary operation that occurs a lot, we usually have a shorter notation than M parentheses A comma B close parentheses. We usually have something like this. So we just denote the binary operation by just some symbol like this, like a dot, or maybe something like this or something like this. You know what I mean?
Yeah.
Okay, so that's what these things are. They are binary operations. The point is that this set of bijections, okay, it has the special property that when you take two of these bijections, it is possible to compose them because the domain and the codomain, they agree. Okay.
Yeah.
So this thing has the nice property that when I take two elements in here, I can compose them and I get a third element in here. Okay, so what that means is that the composition is not just composition of maps, it actually defines a binary operation on this set.
Yeah.
Okay, so I can consider it a binary operation, and so I can give it a name like a multiplication. That's what you might call it. Why is it legal to call it a multiplication? Well, the reason that multiplication, the reason that you can call something a binary operation, the reason that you might want to call it a multiplication is because it is associative. We would not call something a multiplication if it wasn't associative. Now, on the other hand, you might object. You might say, well, but these are not numbers. These are not numbers. They're just some bijections. So why are you calling it multiplication? It has nothing to do with numbers. And you're right. It isn't numbers, but it still has a multiplication. It has a associative binary operation, and that's what we axiomatize as being a group. So we generalize from numbers to arbitrary set that has a binary operation, which satisfies the associative law, and which has inverses. And
that makes sense to me. It's just I wonder if you have a reason for multiplication rather than, I don't know, addition or something.
Well, I could call it addition, yeah, but the
you just like the name multiplication more or something?
So funny. When you go from numbers to more general things, okay, you start encountering different types of binary operations, and some of them satisfy the commutative law, and some of them don't. So there are non-commutative versions of multiplication, And this is a prototypical example. This one here, the composition of bijections is not commutative. So if you compose them in one order or in the other order, you will get different bijections as a result. And there's another example which we're going to study later, which is matrix multiplication of square matrices. That is also not commutative, but it is associative. And so historically, we've just chosen multiplication as the one that is allowed to be non-commutative. But addition, the plus operation, we only typically use it if it is commutative. But you know, it's a convention. It's not. I'm not telling you mathematical facts here. I'm just telling you some kind of historical language. So in groups, when we study groups, it's usually called the multiplication on the group, or the product in the group sense.
All right, I got it. Yeah, that makes sense. Thank you.
You're welcome.
Okay, so I think Jonathan has one last question.
Yeah, this will be the last of the last of the last questions.
All right, can you hear? Can you hear me?
Yes.
All right. Quick question: what happens if you have a map that has the empty set as its domain?
Well, what do you think?
Well, there are no elements to map out, so.
So what is your domain set?
The empty set.
And what is your codomain set?
I'll just say it's also the empty set.
Okay. So is there a map from the empty set to the empty set?
There should be, right?
So what is a map, technically speaking?
Oh, sorry.
So you wanted to ask a detailed, deep question, philosophical question. But now you're stuck because you got to answer it yourself. So what's the domain again?
The empty set.
And what's the codomain?
Also the empty set.
Okay. And what is a map, technically speaking?
Well,
So we said that technically, what is a map? It's really it's a subset of the Cartesian product of the domain and the codomain.
Right.
And that subset, someone said it has to satisfy a condition, which is called what did you call it? Someone called it the vertical line condition.
Yeah, the vertical line test, I think.
Yeah, that's
vertical line
from high
test.
school. Yeah.
Right. So in other words, this subset, whatever it is, okay, it must satisfy a condition that the condition says that for every point in the domain, there's exactly one ordered pair in the graph which has that point as the first element. So in other words, it must satisfy for all x in the domain, there exists a unique element y in the codomain such that x, y is in the graph. This is the so-called vertical line test. Okay, so that's what we need. So we need remember that a function, a map, has a domain set, a codomain set, and a graph, such that the graph satisfies the vertical line test. That's what a map is. So you told me the domain, you told me the codomain. So now let's take the Cartesian product. What's the Cartesian product?
Still the empty set, right?
You answered me with a question. What about answering me with an answer?
Sorry.
Yeah, you're right. It's the empty set. And now I need what? A subset. What can this subset possibly be?
Only the empty set.
Okay, so it's the empty set. And then the question is, so now you've given me the subset. Now the question is, does it satisfy the vertical line test? So let's check it. I mean, how hard could it be? Okay, so for every element in the domain, I have to verify something. And then once I've verified everything, I'm done. So start.
But there are no elements in the domain. So is this just vacuously true?
Well, so it's true. I don't know vacuously true. I don't know what that means, but it's true.
Okay.
Yeah. So the vertical line test holds, and so we've got a function. We've got a map. So there does exist a map from the empty set to the empty set.
All right.
Strange. It's the empty map, I guess.
Interesting. Okay.
Well, some people would call it interesting. Some people would not.
Oh, well.
But
okay.
It's a matter of taste.
All right. Well, that's my question. Thanks.
For the question. Okay, great. Okay, have a great weekend, everyone. And yes, I agree. Thank you, Syed. And let's hope that everyone gets their assignment in on time. Cheers.